Hi, it's Matt, and in this video we're going to talk about how to find the energies using the secular determinant. And to start off, we need to go back and discuss the matrix form of the time-independent Schrödinger equation a little bit more. So just as a reminder, in matrix form, the time-independent Schrödinger equation is given by h vector psi is equal to es vector psi, where here h is our Hamiltonian matrix. Again, operators such as the Hamiltonian are represented as matrices. Then E on the right-hand side is going to be our energy, which is going to be a scalar. And then we have S, which is our overlap matrix. And finally, we have our wave function, or our psi vector, and this represents the wave function and is a vector. So again, in the matrix representation of quantum mechanics, the wave function will be represented as a vector. However, as a slight caveat to that, when we use this formula in practice, rather than subbing in the wave function vector, we'll typically instead sub in the coefficient vector, which is really the coefficients in front of our basis functions. So the first thing we're going to need to do is rearrange the time-independent Schrödinger equation. So again, we start with h psi equals es psi. Here you notice I replaced the wave function with that coefficient vector. And again, that's because in practice, that's what we're going to want to use. But now we want to rearrange it. So I'm going to start off by moving everything to the left-hand side. So that would be h coefficient vector minus es times the coefficient vector. And that's going to be equal to our 0 vector. Or after factoring out, h minus es times the coefficient vector is going to be equal to 0. And again, the 0 here is the 0 vector. And note that sometimes you may see this instead as h minus ws instead of h minus es. That's because the energies we're computing here are with the variational theorem, and sometimes we use w for the variational energy. But again, to avoid confusion, this w here is the same as the e and just represents our energy. And now there are two ways our above equation, referring to this guy here, can be 0. One way is we could have the coefficient vector be the 0 vector. However, since our wave function is composed of these coefficients times our basis functions, that would mean that the wave function itself is entirely 0. And that's not possible, because the wave function cannot be 0 everywhere, because we know our electron or our particle has to exist somewhere. So instead, the only other way this could be true is if the determinant of our h minus es is equal to 0. And again, remember this quantity, h minus es, is going to be a matrix. So, and just as a quick note for terminology, this left-hand side, so the determinant of h minus es, we call that the secular determinant. So now, before we could actually solve for the energies, we need to make a few more notes, such as how many energies our secular determinant equation will give. So remember, we're looking at this equation, and remember that if we have an n basis function, so chi1, chi2, and so on up to chi n, then our Hamiltonian matrix and our overlap matrix will be n by n matrices. So remember, n basis functions, n by n matrix. And in quantum mechanics, the energies we obtain will be real. So putting this all together, when we solve our secular determinant equation, which involves an n by n matrix, we will obtain n not necessarily distinct energies. And what I mean by not necessarily distinct energies is that we could end up with a multiplicity greater than 1. So for example, let's say when we solve our secular determinant equation, we get something like e squared times e minus 1 is equal to 0. What we find then is that the energy is equal to 0 has a multiplicity, I'm just going to abbreviate, of 2. And then we get the energy equals 1 has a multiplicity of 1. And what this means is that there are two states where the energy equals 0 and one state where the energy equals 1. So in quantum mechanics, a multiplicity greater than 1 means that there's some degeneracy in the state, or there's multiple states with that energy. And finally, note that when we have n basis functions, this allows us to compute the lowest n energies. So what I mean by that is, of course, when you have a lot of orbitals combining or you have a complicated system, you're going to have a lot of different energies. But using the variational principle, which gets us to this H minus ES matrix, we can only estimate or obtain the lowest n energies based on the number of basis functions. So for example, if we have a system where we use 3 basis functions, chi1, chi2, and chi3, we will be able to get the ground state energy, the energy 1 level above the ground state, and the energy 2 levels above the ground state. So 3 total energy levels. We will not be able to obtain anything more. So now with all of that out of the way, we can now actually talk about how to find the energies. So there's going to be 5 steps to do this. The first 2 kind of go together. We're going to find the Hamiltonian matrix H and finding the overlap matrix S. This I'm going to assume you know how to do from the previous 2 videos. If you haven't seen those, you might want to check those out if you're not sure how to do this. Then for step 3, we're going to want to compute H minus ES. And remember that the energy is a scalar, and then the H and the S are the matrices obtained from steps 1 and 2. Then in step 4, we're going to want to compute the determinant of H minus ES and set it equal to 0. And then finally in step 5, we're going to solve that equation we set equal to 0, and we're going to actually solve and obtain the energies. So let's try an example. We're going to do it when we only have 2 orbitals, or excuse me, 2 basis functions that we're going to call chi1 and chi2, and we're told they're normalized. We're also given this information. So the first thing we're going to want to do, step 1, is to find the Hamiltonian matrix. Since we have 2 basis functions, we know that we're going to have a 2 by 2 matrix. And from my finding the Hamiltonian matrix video, we know that up here, chi1h, chi1 is going to be the top left element, because on the left we have I equals 1, so that's the row, and on the right we have j equals 1, so that's going to be our column. So row 1, column 1, we know is negative 1.3. Similarly, we're given chi2h, chi2. That's going to be row 2, column 2, so also negative 1.3. And finally, we're given chi1, Hamiltonian, chi2. So this is going to be I is equal to 1, j is equal to 2. So that's going to be row 1, column 2, or negative 1.0. And we know that the Hamiltonian matrix always needs to be symmetric about the long diagonal. So we know in the bottom left, we also need a negative 1.0. Okay, now what we're going to do is we need to go to our overlap matrix. And for our overlap matrix, we know it's also going to be a 2 by 2. And the reason is, again, because we have 2 basis functions. So the only information we're given for overlap is this here, that chi1, chi2 is equal to 0.3. So since I equals 1 and j equals 2, we knew that was going to be row 1, column 2. And from symmetry about the long diagonal, we know that the bottom left will also be 0.3. However, we're not actually given chi1, 1, which we want for the top left, and we're not given the bottom right, which is chi2, 2. However, we're told that chi1 and chi2 are normalized. And that means that chi1 is equal to bracket chi2, and that's going to be equal to 1. So we can now plug those in. And now we've successfully found our Hamiltonian matrix and our overlap matrix. So I just reiterated those on the top right, and now we're going to go on to step 3, which is to compute H minus ES. So the first thing we're going to want to do is write H minus ES and then plug in our Hamiltonian matrix for H and plug in our overlap matrix for S. You'll notice I just left E as E for now, as that's a scalar. The next thing we can do is when we have a scalar outside of a matrix, we can multiply it to all terms inside the matrix. So to get from here to the next step, I multiplied E by all 4 parts of the matrix. matrix. And finally, when we subtract matrices, we do it element by element. So for example, we would subtract, to get the top left, it would be minus 1.3 here, minus E. So we see that up here, it was minus 1.3 minus E. And we would just go through element by element. And finally, we get this as our full H minus ES matrix. Now I just reiterated that on the top right again, and now we're going to go on to step 4, which is to compute the determinant of H minus ES and set it equal to 0. So we're going to write determinant outside of it, and then basically just rewrite our matrix with DET on the outside of it to show that we're taking the determinant. To take a 2 by 2 determinant, we're going to take the long diagonal going this way and multiply those two terms together. And then we're going to subtract the terms going on the opposite diagonal. So if that's a little confusing in words, in math what that would be is, just let me erase these again. What we would end up having is that we would take the top left and multiply it by the top right and put the terms here and here. And then we would subtract the terms along the opposite diagonal. So we would put this term here and this term here. Note that if we have a determinant bigger than 2 by 2, this gets a little bit more complicated, but for here we can go with this for a 2 by 2. And we notice that in this case, this term is equal to this term, and this term is equal to this term. So what we end up finding is that when we subtract them, we get the determinant of H minus ES is in parentheses negative 1.3 minus E squared. Then we're going to subtract negative 1.0 minus 0.3E, again in parentheses, squared. And then the last thing we want to do, as it says in the name of the step, is we want to set it equal to 0. So thus we have set our determinant equal to 0, and we could go on to the final step. So again, in the top right, I put this equation, and now we just need to solve this equation for E to get our energies. So I reiterated the equation here, and then I moved the second term to the right-hand side. And we're left with this equation here. And now from here, you could potentially do some more to solve this, but what I'm going to do is at this point, I'm just going to plug this into a graphing utility or Mathematica to solve, and we find two energies. We find E1 is equal to negative 1.76923, and again, the unit is going to be Hartrees here. And then we're going to find a second energy, E2, is negative 0.428571, and the unit is also Hartree. So these are this is an estimate or a solving for our lowest two energies. And the reason why we only obtain the lowest two energies is because we only use two basis functions.